Okay, welcome everyone. So today's lecture is on OPAMPs. In your previous, courses, you might have heard about this term, but if not, that OPAMPs stands for operational amplifiers. It's a very important component used for numerous electronic signal processing. Analog and digital both. So in this particular lecture, we are going to get the required very important details relating to operational amplifiers. Okay, so let's carry on. So just as a basic, as we understand about different electronic components, they have equivalent symbols. So this, what you see here is the symbol of an operational amplifier. So let's try to understand this symbol, because you need a firm kind of grounding to get a kind of a clear understanding on any particular concept. Okay, so this is the symbol, and in this symbol you can see these are inputs, two inputs. Okay, one is connected with the negative sign and one is connected with the positive sign, and one output. So this negative input for operational amplifier is called inverting. So remember this. So negative input for an operational amplifier is called inverting input, and the plus port of the input is called non-inverting. So that is important as we go along and progress to understand the basic popular features and functionalities of operational amplifier. Okay, so let's carry on. So this is kind of a block diagram of the internal functionality and how it's implemented in an operational amplifier. So again, inverting, non-inverting, two inputs, and it goes into a differential amplifier, which is further connected to a voltage amplifier. So differential means the difference of the two, amplifying the difference, further amplifying the voltage, and then at the output stage, any amplification required. And the important thing what you know here, that the output is connected as a feedback mechanism, both for the non-inverting and for the no, but this is only the power supply. So this is not the feedback, but the feedback is connected. So this is the negative supply voltage connected to all three blocks. This is the positive supply voltage connected to all these three blocks. So, but you see, the arrow is not in these three blocks. Okay. So, but we will learn what I just meant by the feedback. So there is a feedback connections between the three blocks, which basically achieves what we know as an operational amplifier's features. Okay, so let's carry on. So these are the basic packages, IC packages you can find. The popular known ones like LM series, LM74. This is the kind of a metal can package. This is a dual inline package for LM4 741, very popular, especially used in for educational purposes. Historically in industry as well, but in industry they, depending on the application, they are very inclined towards using instrumentation amplifiers for commercial vendors. Yeah, so different IC packages relating to operational amplifier. Again, the symbol, the internal functioning block diagram, and the IC packages relating to OPAMPs. So let's go back to the history from where it started, and it really basically to me is very important for students to understand from where it started. So basically, the OPAM history goes back to vacuum tubes. So these are all vacuum tubes. But what you see here is the work of Fleming, called Fleming walls, but they weren't amplifiers. They were primarily, invented the work of Fleming, and it's called as Fleming diode. Okay, that's what you see here. It's a very interesting read, important read, and the Fleming earlier work on the 19th century. So it wasn't an amplifier. It wasn't amplifying signals. It was primarily simply used to rectify the signals. Okay? And rectify means behaving like a diode, and I think we are pretty familiar with this term. Okay. The second development in 1906 by Lee D. Forrest, and he is the one who basically introduced or invented a 3-element triode vacuum tube. So again, we are still in vacuum tube, but that 3-element triode in 1906 by Lee D. Forrest is basically the one which is used for amplification. Okay, so as you can see here, this is the design which in 1906 again called a triode, using vacuum tubes for signal amplification. Okay, so I simply, it's a very interesting read, both of these slides, previous one and this one, and I expect students to know, okay, how the OPAMs started with. Will they started as an amplifier application invented by someone, or it started as a rectifier? And so these two, I'm not that interested in you exactly knowing the year. No, that's not the purpose of the course. But at least we need to know what is, how the steps happen towards the core invention of amplification, signal amplification. So it basically started with the vacuum tubes, and now it's basically using silicon chips. Okay, so let's move on. And a triode, this is basically the block diagram of the functionality of triode. Here's the cathode, here's the anode. Okay, assume that there is nothing, there is no grid here. So assume for now that there is no grid here. So what will happen? The electrons coming out from cathode, because that's what the purpose of when we apply voltage, negative to the negative and plus to the plus, the electrons, that's the nature, that the negative goes towards, they flow towards the plus charge. So if there is no grid, so it's a natural flow. So this grid was introduced to accelerate that flow of electrons going from cathode to anode. And that grid, you tell me whether it should be positively charged or negatively charged. I think as a basic electricity course, you know that negative and negative repel. And if it's a positive, it has to be positive, because the intention is to accelerate the electrons going towards anode. So that's why the grid is timely given the respective positive charge, so that the electrons coming out of the cathode shoots towards anode. Why I'm taking that much interest in this triode? Because that's even in current world, many particle accelerators from where the particles gets generated. That is the fundamental, still the principle they use, and they accelerate electrons near the speed of light, and that is the basic principle they follow for acceleration. Okay, So in the simplest block diagram, so that's how this powerful the concept is, which kind of introduced, as I said, Lee De Forest in 1906 for signal amplification. Okay, so let's carry on. So this is historic kind of a picture of an OPAMP using vacuum tubes. So these are the vacuum tubes. So these are all vacuum tubes, as you can see here. And here you see coils, and resistors associated. This is the resistor, and there are multiple connections, but it appears like a high power signal amplification. That's why a lot of kind of I'll say safety measures being taken here. But anyhow, this high frequency inverse feedback amplifier is a typical application of the feedback principles invented by Black, and that was back in 1963. So again, amplifier OPAMPs using vacuum tubes. Carry on. And this is again the mathematical kind of a model. OPAMPs using vacuum tubes. This is the model, and output to input is called a transfer function, or you can call it as amplification, and mathematically that's what it comes down to, mu over 1 minus mu beta, and beta is the feedback I was basically referring to. Okay, we will learn how it works, but again I'm just talking historical perspective, and that is in the sketch made in 27 and provided to this gentleman in 77. But again, just kind of a basic historical perspective of the operational amplifiers using vacuum tubes. And this picture is 1953. So we are still in vacuum tubes, but this is when the magic happens, and it's done by this gentleman, Robert Widler, okay, in 64. The first widely used analog integrated circuit is introduced. So this is what they did. They put the analog circuit on a silicon chip. Okay, so as you can see, this is in 1963. And this gentleman, is an LM10, was a very famous operational amplifier, and he was basically looking at its layout before, design layout before producing the respective silicon chip. So from vacuum tubes, we came to these integrated circuits on a silicon chip, and that's why the size, because the desired was. What was the issue in vacuum tubes is again the size and the heat dissipation, and the size was the two primary kind of concerns in relating to increasing the adaptability of OPAMPs or amplification needs in different applications. So that was a very milestone work by Widler. Okay, let's carry on. So that's LM10, again the pictures on silicon. So let's carry on. Again, this is just a zoomed in version of the LM10. And National Semiconductors, still the company, very kind of well-known company relating to producing numerous electronics ICs. So here nowadays, when we talk about OPAMPs, the mathematical model is this what this slide is showing. Okay, this is the model of an ideal operational amplifier. Okay, so it's very important to understand this before, and once you understand this, everything else will be just KCL and KVL, Kirchhoff's voltage law and Kirchhoff's current law. It's all about node analysis. Okay. So what are the assumptions? The basic ideal op-amp assumptions are that the input current IN is 0. So here this, yeah, see the input current is, you say the IB, but that is equal to IN. So the input current is 0. Why input current is 0? Because we are assuming the impedance Zin. This impedance we are assuming to be infinity. So if infinity, it means there is nothing, no connections. So it means that's why the current is going to be 0. Input offset voltage is 0. So this is the offset voltage. So we are assuming that whatever the voltage is coming into this inverting input is the same as to the non-inverting input. So that's why the offset voltage between these two inputs, VE, which we also call it as VOS, is equal to 0. Okay. Then and we assume that the output impedance is 0. So it means this impedance, the output impedance, is 0. So that basically give us a gain, a amplification gain of infinity. Why gain as infinity? Because when we talk about gain of a system, in this case operational amplifier, we talk about V out over V in. So if V out over V in, if V in is 0, so obviously the gain is infinity. So that is what they mean here. But again, these are the basic ideal op-amp assumptions. And why we make such assumptions? Because this will help us do adequate adequate and easy mathematical analysis, mathematical signal analysis, and for the respective circuit. Okay, and we will see how it does it. Let's carry on. So again, reference link from Texas Instruments, and it's basically just bringing this model down to further simplification, that you have a non-inverting input, inverting input with a Z in. EI is basically the gain, whatever happened, and the output impedance, and so E out is equal to minus A EI. EI is basically the input voltage. That's what you see here. But again, further into that, if you talk about differential outputs, so this is how the model can be. Okay, circuit model of the differential output operational amplifier. Okay. Any questions you have at this time, please do ask, and before we proceed, because these are the basics, these are the basic assumptions which put forward in this particular slide for everyone to be very clear that what we will do in analysis in the onward slides. Okay, so let's carry on. Yeah, so this is basically what I was, this is the simplest, that since the impedance is infinity, so there is no connection here, and output impedance is 0. So this is how you basically, you can convert this into this particular block. So E out means the voltage out is equal to minus A times the voltage in, and these are basically the reasons, or the basic assumptions what we do in relating to this particular model. So now this particular slide, I think, is very very well will give you a basic further clarity on analyzing or basically driving the equations for the basic circuits using OPAMPs. So what you see here is that again the input voltage IB is 0, because we are assuming that there is infinite input impedance, and again the assumption is that whatever there is 0 offset, so it means 0 offset means the V in coming in here is same as V in here. So that's why you see V in here. So when V in is coming to this node, okay, so the output is just simply a voltage divider. Okay, so it's a very simple equation that the V in is very easy to drive. This equation is nothing more than, as I said, a voltage divider, where V in you will find that out is equal to V out and RG divided by RG plus RF. RF is for the feedback, we call it the feedback resistor, and RG we name it as a gain resistor. And again, to see their transfer function, so V out over V in is equal to, basically it's very simple, you just flip it, and you can further write it down in this way, like 1 plus RF over RG. Here, if so in this gain equation, if you see when the RG becomes very large, okay, like if this value is significantly large, so the overall effect of that RG being large is that this ratio will be you can consider that to be near to zero. Okay, so that's what it's referring to. And when this term becomes zero, then your gain will be 1. In that case, we consider such a circuit arrangement as a unity gain kind of an amplifier. So that's why then the V out, the output voltage, is equal to voltage in. Okay, so remember this. So let's carry on. So in this is the basic analysis of an inverting op-amp. So because as you can see, the V in is connecting with the inverting input of the operational amplifier. Again, KCL, you see here, the current coming in is I1 from this side, and at this node it splits, coming here IB, going I2 on the RF, which is also, as I mentioned before, is called feedback resistor. And because the offset voltage here is 0, so the IB current going in here has to equal the current on the non-inverting input side. And the direction of why the direction is opposite is because the node analysis, the current coming into a node has to equal the current going out. So that is the direction of the currents. So with this particular clarity of how this picture has been drawn out, you can simply, very easy to find out that I1 is equal to V in over RG, which is equal to I2 minus I2 is equal to minus V out over RF, and to find the gain, which is V out over V in, is equal to minus RF over RG. So this is the basic equation of a non-inverting op-amp. Okay, so any questions you have relating to these equations, please ask now or in further office, lecture, and lab time. So let's carry on. So again, this is another voltage followers which we already discussed it. And what are the key takeaways for the voltage follower or unity gain amplifier? Has 3 ideal characteristics. It has an infinite input impedance. We already know that's one of the assumptions when we do mathematical modeling of an op-amp. A 0 output impedance and a gain of 1. Okay, the practical model can closely approximate this functionality. Okay, so let's carry on. So again, from another reference, some very kind of easy to understand the basic circuits using op-amps. This is in inverting because here E in basically is voltage in, converted, it's connected to the inverting input, and this is a non-inverting, so that's what you see, the E in is connected to the non-inverting input. This is also called as a summing amplifier, and we will discuss further its mathematical equation and the subsequent. But whenever you see multiple resistors connected add the inverting or the non-inverting inputs, most likely that is, using an OPAMP, most likely that is going to be a summing amplifier. So it basically sums up the voltages and amplify it. And the feedback resistor is the very important reason behind that amplification. And this is a high pass filter, and I think I already mentioned it in numerous lectures in the past. This is basically a passive. If you do not consider any, like this section, if you do not consider this op-amp section here, so this is a simple passive high pass filter. But since it's connected with an op-amp, so that because it amplifies the signal, whatever is coming in, so that's why it calls an active high pass filter. Okay, so we will also see the low pass variations of an op-amp. This is again the same thing. This particular RC is a low pass filter, and it becomes active because of the amplification here. So that's called active low pass filter. This is the difference amplifier, and 2 voltages applied together, both at the inverting and the non-inverting. So it's going to amplify the difference of the voltage, and that will become available to the output. And this is basically a band pass version of an active band pass filter using op-amps. Okay. I do not expect you to have kind of will be tested on such a that draw the band pass filter, an active band pass filter, or any of this, or to draw any of these circuits. What I want you to know are the key concepts. Okay, like as I said, if you've been given a circuit like this, what you will conclude by just looking into the circuit is it called a summing amplifier or a difference amplifier? Is there an active low pass filter, or if it's an active high pass filter? So what kind of a circuit that is? So I think in this particular course relating to microelectronics, that is important concepts you can be tested on. So this is another kind of I found it very kind of a useful information to share with, basically a current to voltage converter. And again, using an op-amp, that's from Maxim 41. Maxim is a popular company, but this is a Max 4122 IC. So the current coming in, consider the circuit at the input of the op-amp. The current flowing towards the input pin is equal to the current flowing away from the pin. Since no current flows into the pin due to the input impedance, so it means the current going in is same as the current coming out. Again, these are the assumptions, mathematical assumptions, but very important ones to keep in mind. Okay, the same cannot be said for the output. So the op-amp can source or sink current. So here, if you consider this as node, okay, so the current will split here. So let's say you consider this as I1 and this as I2. Because this I1, no current can go in here, so this is 0, so it means the entire current will flow into this RF resistor, but that flow is not unidirectional because this is also connected to the output, so the current is also coming back. So that's why I put in this slide. So, and again, further on to this, a simple current to voltage converter is shown in this figure. Its behavior can be easily understood using the previously explained node analysis. And again, this is that's what it does. That V is equal to it's the same current coming in here, V in R, and the output is basically is going to be Vref minus Vn. So that is kind of another. I found this as a good description of basic analysis using op-amp, but we have already done in the inverting and the non-inverting section of it, all of those equations to make clear sense to it. But in this case, we are just trying to understand that if you are dealing with current rather than voltage at the input. Okay, so let's carry on. So this is the difference amplifier. I think we already discussed about that in our previous slide. Um, and in this case, like again, similar equations, but what we have seen previously. So I really want students to basically, just read it and make sure that they understand, the equations relating to difference amplifier, inverting, non-inverting, and other what we will discuss. But this is kind of a detailed derivation of a difference amplification, which basically comes down to this equation. And then further on to, as we see here. So in other words, the output depends on the difference voltage across the input and the gain settings resistor as we could expect. I do not expect in this particular course, because there's a course relating to microelectronics, for students to drive in equations like this. No, that's not the purpose. But you need to know this equation. So this is the most important thing. Okay, so G over here is basically the conductance, which is 1 over R. So if I go back here, you see this, so the G's are 1 over R. R is resistance, and G symbol is used for conductance, reciprocal of resistance. So if you just replace G1 and G2, so you basically comes this term will be R2 over R1. Okay, so I want students to know, write it down, and remember this term. Okay, that if I give you a voltage at the non-inverting input and at the inverting input with proper resistor values, you should be able to find me the output voltage, or any of the parameters I give you and ask you to find any other parameter. You should be able to do that easily at this particular course level. Again, another very good kind of I'll say diagram relating to the basic concepts of operational amplifier. Not only the basic concepts, but some of the very important notations and terms used in relating to operational amplifier. So this is the input voltage, okay, and this is the input resistor, this is the feedback resistor. We already discussed that. This is the summing point. So that is very important, at the at the inverting input, this point is called the summing point. And this resistor used at the non-inverting input is for the stabilizing, drift stabilizing feature. And that resistor is optional, again, depending on the applications environment, whether you do need and what should be the value of this stabilizing resistor. And here is the output voltage. Okay, so this is basically that's what we in our mathematical analysis to drive the equations is our feedback loop. Let's carry on. Let's go back here. I think we clicked this, but then again, that's a good example for anyone to go to a certain reference. If you see the hand, you just click there, and you should be able to go to that particular reference. That's the hand. What I mean, because I think we clicked, and that's why it was to that page. And again, this is the silicon wafer of an OPAMP. The silicon. This is the silicon circuit put on the wafer of a silicon chip. Okay, and the material can be silicon and germanium, but in this particular slide we are seeing one of the popular LM74 kind of a circuit diagram which goes inside that particular chip. This is the non-inverting input and offset null. This is the output. This is the negative supply, and this is the positive supply. And here's the inverting input, which I was trying to find out somewhere here, but it's right here. So this is the inverting input, this is the non-inverting input, the output, and the plus and negative voltages. Let's carry on. Another example, just to show you, I'm just trying to show you in these two slides is that so much complexity is being taken care by engineers to give you the comfort of ease in use to achieve the desired objectives, which is amplification, can be filtering, can be current gain, whatever it is, using OPAMPs. And this is the 741, very popular OPAMP in academia for practicing OPAMP circuit design and analysis. Again, an inverting amplifier example. I think I already discussed it, but since these slides I found it very, kind of, everyone has its own way to describe the concept. So these, very, I'll say very good read for students to go through it. But we have already analyzed it in the beginning, that how this equation, we drive from for the inverting case as V out is equal to minus R2 or minus V in times R2 over R1. And so here what I want, so I'm going to take a little pause here. So I want students to calculate, because the values are given, okay. So I want students to calculate the output voltage for input voltages going from 1 to 5 volts, and let's see if we can find out that what should be the power supplies. Okay, this is the negative power supply, and this is the plus power supply. So I want you to calculate this output voltages, again going from 1 volt to 5 volts in stepping 1 volt. So 1, 2, 3, 4, 5. So let's see if we can do that. Again, this is the non-inverting amplifier, another way to describe, as we have already derived this equation, that how this non-amplifier equation drives this particular form. And this is the summing amplifier. Okay, so as you can see here, we have V1 voltage, V2, but it can be going down like V1, V2, and all the way to Vn. So all those voltages, when we do the mathematical analysis, so this is what we get them as an output equation. So in this case only two voltages, so V1 plus V2, okay. And but I can in an exam or quizzes, I can give you 3 voltages or 5 voltages and be able to ask you to find out the output voltage, or I can give you the output voltage, the feedback resistors, and some of the voltage, and I want you to find out any of the input voltage. Either way around, you should be feeling yourself comfortable in achieving those objectives asks in a particular question. Carry on. Yeah, so please go ahead and practice this. And again, in this particular case, I want you to consider your VI1 as 500 millivolt and VI2 as 1 volt, and see what you will find as an output voltage. The resistor values are already given to you. Okay, so let's carry on. So this is the difference amplifier. We already discussed it, and I have to drive this equation again because I really liked this, the way they described it. And the reference link is already shared with you, I think, in one of the previous slides. The reference is there. But if you just simply Google it, UCSD physics, and you should be able to find this particular slides where I took it. So this is a differentiator or a high pass active filter. Okay, and whenever there is a component like a capacitor or an inductor, we are talking about differential equations. So we already know this is the basic equation for when we deal with capacitors. and the current in a cap is basically a rate of change of charges. Okay. um, uh, so long story short, if you apply the signal, if the signal is, let's say this is VO sine omega t, omega is 2 pi f, as you know. So the output voltage will be is basically you differentiate that, and that is the equation, mathematical form. V out RC omega cos omega t is what will be the output for that differentiator or high pass active filter. And omega depends means higher frequency amplified mode. That's what it is. And again, just to show you this, that a high pass active filter, one of the variations of it. So let's carry on. Again, this is a low pass active filter, also called integrator. So at least in this particular course, you need to understand that when you talk about a low pass filter, it's the term in an OPAMP is an integrator, and when we talk differentiator, it's a high pass active filter. And the reason we call it as integrator, because it's a mathematical term, as you can see here, the integration. The output voltage is basically an integration of the input voltage. Let's carry on. Yeah, so I would like all of you to practice and find the values, of the respective values, because the resistor values are given. Okay, this is the unity gain. Skip this one. But this is also a kind of a snapshot of what we discussed in the previous slides. Unity gain, summing amplifier. This is inverting amp, and this is the non-inverting amp. Okay, so this is basically a sum up. I think if we haven't done all the calculations in our class time or lab time, I would like you to do that, and we can take a pause here as we progress and find out the output voltages. So let's carry on. So this is doing and the complete transfer function of the circuit. It's basically again driving the equation to what we have already done. Okay, so these are the so any questions you simply ask. So but in this particular case, is what's happening is the VREF is connected here, and again it's very simple. Just make those assumptions that the input impedance is infinity, output is 0, and then you'll be able to find this equation, and which you can further reduce to this particular equation. It's not expected that I'm going to give you this particular circuit and ask you to drive this equation. No, this is not the purpose of this particular course. So let's carry on. Why is feedback used in OPAMPs? And then that is the most important, I'll say, the point, because whenever you see an OPAMP, you always, most of the time, there is a feedback. Okay, there is a feedback resistor or there is a feedback wire connection. So for feedback wire connection, I mean when there is a unity gain. That's what it is. So let's understand this. So typically OPAMPs have an open loop gain on the order of 105, which is roughly around 100 dB. Without feedback, OPAMPs make circuit design difficult because of high gain sensitivity. Negative feedbacks make it possible to set the gain and cutoff frequency to the desired values, thereby improving their stability and reducing performance variations, part-to-part variation, and sensitivity to temperature and other environmental parameters. But the most important thing, as I said, in these all feature parameters is basically because the gain is very high, so it means the input primarily is going to clip at the output. So that's why the feedback is very important, so that we can control the gain. Okay, we will see it pictorially in the graph here. That's how the researchers show their work in publications. So what you see here, that so this is an open loop gain. So the curve, as you can see here, Before going to the graph, understand this. We are talking frequency here. Okay, this is the frequency axis, and this is the phase degree and the gain in dB on this side. So if there is open loop gain, so you see this line will go, keep on going and be very high. Okay, but this is the line which, because of the feedback, we call it as a closed loop gain. We don't want the clipping to happen, or these kind of instability to happen. So to stabilize it, we just close it here. Okay, and this is the phase portion of the signal for the inverting amplifier and for the non-inverting amplifier. Okay? So in simple words, if it's still kind of difficult for you to understand or envision this particular graph, in simple terms, the feedback resistor is there is to control the gain and stability of the overall circuit. Let's carry on. Yeah, so that's another very kind of a nice graph. So you see here that instability region, or kind of a open loop gain, we bring it down to the stability point of what we call it as closed loop gain. So in this particular we achieve wide bandwidth. Okay, so we have stability in this particular wide band. Yeah, so that's another good document which I found relating to operational amplifier from Texas Instruments. And this is an instrument amplifier. Why I'm showing you here is that because instrumentation amplifiers are widely used in the industry, and they provide significant gain by just using a tiny IC, very easy to configure. And this is one of the internal kind of a circuit within an instrumentation amplifier. So as you can see here, it's using 3 OPAMPs within one IC in order to achieve, as I said, significant gain. But your gain is, I think I already told you, cannot go beyond the supplied voltage. Okay, so the gain will be limited to the applied voltage. Very important, both plus and negative side. But when depending on your application needs, you make sure that you use the proper supply voltage to achieve the desired objectives. Okay, so some of the design notes are taken from the same document that use precision resistors to achieve high DC common mode rejection ratio. So this is the concept relating to OPAMPs. Okay, performance. R10 set the gain of the circuit, add an oscillator resistor to the output stage to drive large capacitive loads. High values resistor can degrade the phase margin of the circuit and introduce additional noise in the circuit. Linear operation is contingent upon the input common mode and output swing ranges of the discrete OPAMPs used. The linear output swings ranges are specified under the A01 test conditions in the OPAMPs data sheets. So in simple words, they are trying. So we are discussing basically instrumentation amplifiers, and this information which I have taken is basically from within the data sheet or relevant design notes of of using this particular op-amp. So showing you here is very important that whenever you use an IC, any IC, in this particular case operational amplifier, make sure that you understand the relevant important design notes given to you before you use that particular IC in your circuit. To further ease in using the ICs is that they always provide the relevant chip manufacturer, what they call it as the reference design or designs. And so basically make sure that your starting point can also be your reference design provided to you by the IC or the OPAMP, in this case manufacturer. Okay, so this is a Vein bridge oscillator. So and why it's an oscillator? Because you can see here it's an RC here, and this is its analysis. This comes down to basically using Laplace transforms. But I'm just trying to show here that what this the output of such a Vein bridge oscillator look like. So it's basically in this particular case, as you can see, there is no signal, but because of this RC component here and the RC as a feedback, you can get the harmonic kind of a sine wave at the output. Okay. So the technique of node analysis can be used as we are. Okay. So what? Yeah, so it's basically all the mathematical description. Anyone with the passion, please go ahead and read it. But I just wanted to introduce and tell you relating to OPAMPs that how it can also be used to generate a periodic signal at the output. And this is the work of Mr. Wayne. Okay, let's carry on. Again, the same read. So what are the conclusions in this slide is that that KCL, the currents flowing into and out of the node around the op-amp, can be translated into equations and form. We already have done it. I think it's kind of the same replica I've taken from different sources. But to reiterate this, if your basics are strong and if you have enough practice, if you have done enough practice in your homework, okay, so it's very easy to understand primarily any concept, not necessarily op-amps or microelectronics or microprocessors. You can be anything you want to be. Okay. So these are the references. So thank you very much, and we'll carry on meeting our next session. Take care.